A DePIN network only becomes valuable when users can trust it. Devices need to resist attacks, data needs to stay private, and services need to keep running. In this section, we'll look at how those requirements turn decentralized infrastructure into something businesses can rely on. So far, we've built the foundation: markets, incentives, governance, devices, proofs, and data flows. Now we move into technical trust: how DePIN networks stay secure, private, and reliable enough for real-world use. In DePIN, trust is not one control. It is a chain that runs across devices, users, off-chain infrastructure, and blockchain logic. Security helps prove devices are real and rewards are accurate. Privacy protects sensitive signals like location, usage, and telemetry. Reliability keeps the service usable when customers depend on it. If one layer fails, the impact can spread quickly: lost funds, exposed data, outages, or loss of confidence. Strong DePIN design treats these pieces as one connected system. Device security is the first layer. Unlike servers locked in data centers, DePIN machines may sit in homes, streets, vehicles, or remote sites. That makes physical attacks realistic. If someone steals a device, changes its firmware, or spoofs its identity, the network may accept bad data and pay rewards to the wrong actor. Firmware is the device's root of behavior. It determines what the hardware senses, computes, transmits, and proves. That means trust has to begin before the device fully boots. Secure boot checks that only authentic firmware can run. Updates should be signed, staged across the fleet, and protected from rollback to vulnerable versions. After deployment, operators need version visibility, patch tracking, and emergency update paths. Otherwise, the update system itself can become the easiest way to compromise the network. A device should not be trusted just because it connects. Trust starts during provisioning, when the device receives a unique cryptographic identity. Its private keys then need protected storage, such as a secure element or trusted execution environment. Before submitting proofs or earning rewards, the device authenticates to the network and encrypts its data. Over time, key rotation and revocation help keep cloned, stolen, or compromised devices from remaining valid. Security also requires an uncomfortable assumption. Not every node is honest. A single operator may create many identities, report fake sensor data, or claim coverage from devices that are duplicated, moved, or never existed. Fraud detection cannot rely on one signal. Strong networks combine cryptographic proofs, behavior patterns, reputation history, and real-world validation. When abuse is confirmed, rewards can be withheld, nodes blacklisted, or stakes slashed to make cheating economically irrational. Communication security protects every hop: device telemetry, control commands, proofs, and customer data. Encryption keeps traffic private as it moves through gateways, APIs, cloud services, and blockchain-connected applications. Mutual authentication makes sure both sides are legitimate, not rogue gateways or fake services. Segmentation limits the blast radius when something is compromised. Rate limits, DDoS controls, and anomaly detection help keep the network available when traffic becomes hostile or abnormal. A useful privacy model is the data shadow. DePIN devices may only report signals like location, timestamps, sensor readings, wallet activity, or usage frequency. But together, those signals can reveal much more: where someone lives, when a facility is occupied, how vehicles move, or where demand is rising. Even anonymized data can become identifiable when matched with public blockchains or outside datasets. Privacy risk is not just the raw data. It is the inference others can build from it. Privacy-preserving DePIN starts by collecting less. Gather only the data needed to verify activity, deliver the service, or measure performance. Then make consent meaningful. Users should know what is collected, why it matters, and how it will be used. Anonymization and aggregation can reduce identifiability, but they are not magic. Re-identification risk still needs testing. Finally, define retention rules. Delete data when it is no longer needed, and restrict access throughout. Enterprise adoption changes the control model. A community network may rely on openness and broad participation, but a business customer needs proof, restriction, and accountability. That means role-based permissions, clear audit trails, defined retention rules, and control over where data is stored or processed. It also means security reviews, compliance evidence, and operating procedures the customer can trust. For DePIN, the challenge is preserving decentralized infrastructure while wrapping it in governance enterprises can actually buy. Reliability is what turns a DePIN network from an experiment into something customers can depend on. Uptime means the service is there when needed. Redundancy means no single device, gateway, region, or backend can break everything. Failover means work automatically moves around failures, whether they come from hardware faults, outages, bugs, or operators leaving. For DePIN networks, reliability comes from closing the loop between detection, diagnosis, action, and learning. Monitoring shows when device health, latency, proof validity, data freshness, or APIs drift from expected behavior. Observability gives engineers the evidence through logs, metrics, traces, and alerts to find the root cause. Incident response makes ownership, escalation, and customer communication explicit. Afterward, post-incident reviews turn failures into stronger systems, better thresholds, and fewer repeat disruptions. An SLA turns network performance into a promise a customer can buy. For example, a logistics firm may require 99.5% sensor data availability across 5 metro areas. That requires clear definitions for uptime, response time, accuracy, coverage, how each metric is measured, and what happens if targets are missed. In DePIN, this is harder because supply is decentralized and coverage varies. Enterprise trust requires auditability, remediation, and operations behind the incentives. Trustworthy DePIN networks are built in layers: secure devices and keys, protected data, and reliable service under real-world conditions. These foundations turn experimental infrastructure into production systems. In Module 4, we'll connect that trust to go-to-market strategy, operations, regulation, and adoption.